AP physicists. I just wanted to look at this problem with you. I've got some conservation of momentum problems that you're going to work on today, and thought that this would be a good kind of jumping off point. We looked at this in one class just a little bit, but in the other class didn't at all. And I just want to make sure that the concepts that we talked about yesterday of Newton's third law, his most important, as we know, law, and the result of that, which is conservation of momentum, that it actually is really making sense. We will take a look at this a little bit more on Monday as well, but just so that you've got a sense of kind of what's going on. So this problem says that a 250-gram glider is pushed across a level track towards a 500-gram glider that is at rest. I'm going to draw myself a quick little picture here just to have a sense of really what's going on. So I've got my first one. I'm going to call this the 250-gram glider. I'm going to call that one A, just to kind of keep myself organized here. And it's going to be moving toward, it said, the 500-gram glider. I'm going to call that one B. It's my B. And that one, it says it's sitting at rest. So this is kind of the before picture. And as one would imagine, if you have one glider that's coming in and going to head towards another one, then they're going to interact. When they interact, two objects interacting, forces are going to occur, and as a result, we'll have a change in momentum. So let's take a look at what's going to happen. So we don't really know the total result until we look at the data. So here's my after picture. Now, if we take a look here, it says the graph below shows a position versus time graph for the 250-gram glider as recorded by a motion detector. This is the part of this problem that is really very AP-esque, as opposed to just giving you numbers, which is how the problems are that I'm going to give you later today. But this is really nice because it's got this nice position versus time graph. So position is over here, time is over here, and as you can see in the before part, okay, I've got a constant slope meaning that we've got a constant velocity, and here is the equation of that line. So we can tell from that equation how fast we're going, right? It's a y equals mx plus b. It's already linearized for us. Y equals mx plus b. The slope of a position versus time graph is going to be the velocity of that object. So the initial velocity for cart A, which is what this is tracking, is, it looks like 0.75 meters per second. So over here, and we'll draw this picture again in just a moment, the initial velocity, I'm going to say, for cart A, according to the graph, is 0.75 meters per second. Okay? Now, it says also that it records the motion both before and after. So if you take a look at the second part of this graph, there it goes to a peak, and then it looks like it goes downhill. So while at the beginning it was moving in this direction, it was moving to the right, looks like after the collision, they don't stick together in this case, but that cart, we'll draw it over here, after the collision, here's A, it looks like it's actually going to be traveling in the other direction. So at the end, after the collision, after that interaction, it's moving in this direction. How fast is it going? Oh, well, it says right here, it says that the velocity final for cart A, because we're assuming it's a frictionless, I think it does say, track, okay, or pretty darn close at least, because it's got a constant velocity, is equal to negative 0.21 meters per second. So indeed, it is actually turning around. So this just has the information for cart A. We need to figure out what's going to happen to cart B. So if cart A starts out moving right and then turns around and moves left, cart B is going to have to do something interesting. It can't just sit still, because remember, Newton's third and most important law says that if there's a force of A or B on A causing it to accelerate from going to the right to the left, then cart B has got to have a force acting on it as well. And I'm thinking that that's going to make cart B move to the right. Okay, so if I write down over here the initial velocity for cart B, that one was 0 meters per second. And the question is asking, what is the speed or velocity, right, of the 500-gram glider after the collision? So we are looking for the final velocity. That's our question mark here for cart B. Okay, I'm going to go ahead and add in our masses. We know that the mass of cart A is 250 grams. I really like to do things in kilograms though, friends. So I'm going to go ahead and say that's 0.250 kilograms, right? Because kilo is 10 to the third. And the mass for cart B is going to be 0.500 kilograms. I'm not actually going to use all of those zeros, but for sig figs right now, we'll go ahead and write that down. Okay. So remember when we were doing all of this yesterday, we said that the total momentum at the beginning had to be equal to the total momentum at the end. So we're going to utilize that knowledge and go ahead and run with it. So the total momentum at the beginning has to equal the total momentum at the end. Okay. So that's all well and good. It's hard to just like run with that because I don't know exactly what to do with that. So we're going to break it down into our pieces. So we'll do the momentum of cart A at the beginning, and we're going to add that to the momentum of cart B at the beginning. Just trying to double check my notation here. And I am claiming to you, and I'm hoping that you are with me here, that that's equal to the momentum of A at the end plus the momentum of B at the end. Okay. It's nice because I do see that we've got one velocity that is 0. Momentum is mass times velocity, so that means that the velocity for cart B at the beginning is 0. So that's kind of a nice little deal. And then we just really honestly need to just plug some stuff in. So here we go. We're going to do the mass of A times the velocity initial for A needs to be equal to the mass of A times the velocity final for A plus the mass of B times the final velocity for B. Now, this is kind of a lot of stuff, but really there's not a lot to it. What we know and what we're trying to figure out here, we know everything in this except this thing right here. If you know all the values except one, then it's a pretty easy deal. So we're just going to go ahead and solve this equation. So I've got MA VIA, I could subtract off my VFA, right, because we're just going to move that over, and then divide that by the mass for B. And we should, from that, be able to figure out pretty efficiently what that velocity is. So let's go ahead and plug in some numbers. So we've got 0.25 kilograms, and we've got a change in speed. So initial minus final. So we've got 0.75 meters per second minus a negative 0.21 meters per second. Minus a negative is like plus a positive. And then we're going to divide that by 0.5 kilograms. Let's go ahead and plug in those numbers. You can do this too. Get out your calculator. We'll do some calculating together. So we got 0.25 times 0.75 plus 0.21. Then we're going to divide that by 0.5. And it looks like the final velocity, VF for B, how fast is it going, is 0.48 meters per second. I often like to take a look at these and make sure that that makes sense. So it's going slower than the cart A started out, but that kind of makes sense because it's twice as big. So its acceleration is going to be a lot smaller than that initial one, than A is, because A is only half as big. Okay, so I hope that that helped you to both look at that graph and then also look at the math with it as well. Have a great day and a great weekend, and I'll see you on Monday.